Welcome to our next video on 2D NMR example problems. Here we're going to take a look at, again, a set of isomers that are pretty similar to one another, just with a different arrangement of the pieces. So if you look at these two pieces here, we have an ester in both compounds and an alkoxy group in both compounds, and we just switched around the identity of the ester and the alkoxy group. So they could be very similar looking in their NMR spectra, but they're not exactly the same. So we have to use a little bit more in depth of a technique to be able to determine the difference between them. And the main difference here is in the connectivity of those pieces. We're really going to use the HSQC and the HMBC to hammer home the difference between our ethyl ester group and our methyl ester group and see which one it is. So let's first dive right into this proton NMR, because the splitting of the pieces here is really going to help us figure out which hydrogens are which. The HSQC will help us figure out which carbons go with which hydrogens, and then we can fully label everything at the end. So let's start by labeling our peaks in the hydrogen NMR, just as I recommended previously. We'll start at the highest ppm and start with A all the way to E. So we have 5 different types of hydrogen identities on our molecules, and let's just draw in some tick marks on both of these to make sure that that kind of adds up. So we have this methoxy group here, that's all one type of hydrogen. Then we have another type here, 2, that's 3, and then 4 and 5. So all of these little tick marks are identical within themselves, but they're different from all of the ones across, right? So there's no big plane of symmetry within this molecule. All of the hydrogens are kind of next to some of these other groups. So let's get rid of all of those confusing annotations so that we can start again on a clean, fresh molecule. Okay, so we have A, B, C, D, E. Let's think about the identity of those based on their splitting patterns. So the one that might stick out the clearest, at least it does to me, as being very different from the rest is C. C has no splitting to it, at least not that we can tell from this magnification. So that kind of has to be a singlet, and that means that it has to be something with no neighbors, right? So the only place that we don't have neighbors is here on this methyl group. Depending on which one it is, it's either the methyl ester or it's a methoxy group. All the other ones, like I said, have neighbors adjacent to them, so it can't possibly be those. So we get rid of those circles and instead label that these methyl groups must be C. They have to be. And then we can think about the other ones. We'll just start at A again, going alphabetically. You do it in whatever order makes the most sense to you. So peak A is the furthest downfield that we are seeing in our molecule. And that means that it's probably adjacent to something pretty strongly electron withdrawing. So in this case, for our ester, that's going to be either of these sp3 oxygen atoms. So that kind of narrows it down to either this set of hydrogens here or that set of hydrogens there. How will we tell the difference between them, given that they're both next to an oxygen? We'll be able to tell based on their neighbors. So we look at A. This looks to me to be a quartet splitting, so that must have 3 neighbors, right? And so if we look at this one in the middle here, can it be that one? No, I don't think so. It only has 2 neighbors, so 2 plus 1 would be 3 and a triplet. That's a little bit of a spoiler for where we're going next. But what about this one on the ethyl ester here? That makes more sense. Now we have 3 neighbors, so this set of protons here would be split into a quartet. So let's get rid of these other ones. It must be that group there that is at that ethyl group end of our molecule. So again, remove those annotations and we'll label that as A. Similarly, on the lower molecule, I'm trying to go through and label both of these at the same time because they have all the same pieces, they're just connected differently. The bottom molecule, it has to be, again, that carbon and those 2 hydrogens because it's split by the 3 neighbors that are adjacent. So same pieces, different connectivity. All right, and then thinking about B, B is also pretty far downfield and it is a triplet. So that tells us that it has to have 3 minus 1 is 2, 2 neighbors. That is probably this set of hydrogens here that we were looking at originally. So that's going to be B there, and it will also be B here. Okay, then we have D and E. Let's just keep going in alphabetical order. D looks to be a triplet to me, and it's kind of in a weird position upfield. It's not that high, right? But it's not as low as E. So it must be next to something that's kind of interesting. If you're around 2 ppm, that you can keep in your mind as a baseline that could be adjacent to a carbonyl, right? So being adjacent to a carbonyl, that carbonyl has a partial positive charge, but it's not as strong as being immediately adjacent to an oxygen. So the protons at those types of positions are going to be somewhere around 2. Now that could be a lot of other different types of protons, but it might be a good thing to have in the back of your mind for this current unit that we're in. So based on that, the remaining choices that we have here are that set of hydrogens here or the methyl group hydrogens, right? And in either case, they're going to be the same splitting because A has 2 hydrogens on it here and B has 2 hydrogens on it here. So either of those groups will be split into triplets. So E is also a triplet, but our knowledge of the carbonyl chemistry of that really electropositive carbon center pulling away at that adjacent alpha carbon makes me pretty confident that we can say the alpha carbon to our carbonyl here is D, and that methyl group, the furthest upfield, it's not really very close to anything interesting, is going to be E. So again, we can transfer those same assignments onto the methyl ester down at the bottom. All right, so now we have a feel for where our hydrogens are. We feel pretty good about that. Let's go ahead and move on to the carbons. Again, I'm going to number this starting at the highest ppm with the lowest number and give that to this carbon here, carbon 1, and then we have 2, 3, 4, 5, and 6. And let's just do a little quick sanity check to make sure that that makes sense for our molecules. We have 1, 2, 3, 4, 5, 6 carbons. Yes, we are good. So now we can start to think about the correlations of the hydrogens to the carbons. So I'm going to do this by first just drawing in all of the correlation lines as carefully as I can, and then we'll step back, talk about what they represent, and translate those over to our structure. So to get us started, I'm just going to start over here with E, and again, just like we did in our cozy example previously, just drawing lines down to these peaks as straight up and down as you can get them. And I'm trying to use the help of my iPad software a little bit to make these lines as straight as possible. Some of them I may need to edit a little bit. So I'm going to pick them up and try to move them over carefully. If I can pick it up. There we go. Okay. So move them over a little bit. Some of them don't line up so perfectly, and that's okay. You got to just do the best that you can, and where you see there are a couple of peaks close together, you just want to be extra careful to make sure you've got it as centered as possible. So using the blue, I've drawn down from the hydrogens, and then to kind of keep a little bit of color coding, I'm going to draw red across to the carbons. So starting from this peak here and drawing over, and then kind of waiting for my line to snap. That looks like it goes there. And just following these across. Now you can see this is a little bit of a tricky situation here. It looks like carbons 3 and 4 are quite close together, and that our lines aren't necessarily super clear there. So I think I did pretty well. I am going to try to move these just a little bit. Okay, after a little bit of fiddling, I've done kind of the best I can with carbons 3 and 4. So you see why it can be really, really important to either work on paper with a straight edge or use some kind of straight edge tool in something like PowerPoint or Google Slides to make sure that you're getting these as straight on as possible. And even this is by far not perfect. So we'll work with it and use it to identify our cross peaks so that we can label our structure. So just kind of going along, I'm going to put down the correlations that I'm reading from my not so perfect lines to tell us what these signals correspond to. So if we start kind of over here where we began, near carbon E. If we follow down, there's a peak beneath that. So that looks to me to be an E to carbon 6 correlation. So what that's telling us, and we'll fill all this in more later, is that our E protons are here, that carbon is carbon number 6. So we'll do a nice and not so sloppy jumbled job of labeling those again in a moment. Uh, Continuing on, D seems to correlate to carbon 5. If we come down from C, that seems to correlate to carbon 4. Again, that's a little bit tricky, but you can maybe tell by eye that the spot underneath C is a little bit higher up than the one underneath B. I think this one here is a B to 3 correlation, and here we have an A to 2 correlation. Okay, so that's kind of boring, and sometimes your HSQC will be boring. It seems like, yes, the highest downfield shifted carbons correspond to the most de-shielded and downfield hydrogens. That seems sort of logical, right? But that's not always going to be the case. So you can't necessarily assume that, yeah, hydrogen A is the furthest downfield, so it's probably going to be on the furthest downfield carbon. That's not always true. When we come to talk about that, think about what's going on here with carbon 1, right? That is the furthest downfield carbon, but it doesn't seem to have any correlation peaks in our HSQC. Why is that? Thinking about the number of actual chemical shift that's there, we're somewhere in the 170s. What's the only functional group that gives a carbon that high up in our chemical shift range? It's got to be something with a carbonyl, right? So because of that, we see the high chemical shift of the carbonyl, and there's no correlation in our HSQC because there are no hydrogens here, right? There are no hydrogens on our carbonyl carbon, so we don't see any direct bonding correlations in our HSQC. I'm going to take a minute to quickly draw in our numbers for the carbon and re-letter our letters for the hydrogens so that we have a very, very clear picture of what is going on where. So we said that the hydrogens E are on carbon 6, so I'm going to label this carbon number 6, and I'm going to try to do this as neatly as possible, and then I'm going to alter the hydrogen annotations so that they're a little bit cleaner. D was carbon 5 here. C was carbon number 4. B was carbon number 3. A was carbon number 2. And our carbonyl carbon was number 1. So I'm going to replicate the same here. So that we have nice consistency between our two structures. And then I'm going to go ahead and relabel all of the hydrogens as drawn out bonds to hydrogens so that we have a little bit easier of a time visualizing it later on. Okay, so that's a lot of labeling, but I promise you it's going to come in handy when we get to the HMBC, because we're going to be kind of getting a little bit more of an alphabet soup of a bunch of letters and numbers. It's going to be really useful later to allow us to count the number of bonds that carbons and hydrogens are away from one another so that we can see if the correlations make sense for the top isomer or the bottom isomer. So I'm going to copy these annotations down to our next slide so that we can take a look at our HMBC data. Okay, same thing goes here. First and foremost, letter all of your peaks. We'll draw in our cross peaks, and then we'll get started analyzing what's actually happening with all of these correlations. So starting with our letters for hydrogens and numbers for carbons. We are all set there. And then let's start drawing in some correlations. For these, I'm going to take a little bit of a different approach. I'm going to draw just a long line in blue for the hydrogens and try to match it up with the edge of this spectrum here so that I know that it's straight and that I can just move it along to each possible peak so that I can see any correlations all the way down the length of the spectra. Since there are usually only 1-to-1 correlations in your HSQC, it's a little bit less critical to do that. But you can see that how I've lined up the line under peak A, it seems like A correlates to two different things in our HMBC. So it's going to be best to just draw a nice long line so that you don't miss out on any of those correlations. And this may be a little bit of an eyesore for some who feel visually overwhelmed by the NMR data itself, or just by the fact that there's going to be a lot of lines here. So bear with me if this is not a method that feels comfortable for you to use. Definitely go ahead and use a method that makes more sense or feels easier for your brain to wrap around. Like I say, there are many, many correct ways to approach these types of problems. So now we'll draw a red line across so that we can use it to figure out where our carbon peaks line up to. And again, just gonna move this around as needed. If I can pick it up, there we go. And line it up with our carbon peaks. And again, we're gonna do the best that we can with carbons 3 and 4 because they're a little bit tricky, but I think we can manage it. Okay, last but not least, carbon 1, like so. Okay, so now we've got, again, a kind of a lot of things going on here, a little bit of a spreadsheet look, maybe a little bit of a plaid tartan look. Um, I want to sort through all of these to nail down the correlations that we're seeing, and then we can kind of sift through them one by one to see where they do or don't exist on our ester isomers. So I'm going to fill these correlations in here, wherever I can fit them. And then when we've got those correlations in, maybe we can get rid of some of these lines to just help visually calm it down a little bit more because it is a lot and I think it's going to even overwhelm me a little bit. So just to use these lines as a guide to get your correlations and focus in on what the correlations mean and not focus too much on all of the crazy lines that we've just drawn. So let's start here. If we draw down from carbon A, we can see that we go across to carbon 6. So I'm going to say that this is an A to 6 relationship. And if we keep going down along A, we see that A also corresponds to 1. So let's fill that in. That A is going to relate over a 2 to 3 bond coupling to 6 and to 1. So that will definitely help us as we figure out which of these two isomers that we have. Let's keep going. B here seems to correlate to 5. And if we continue down the line, it also seems to correlate to 4. I think I did a little better of a job with the lines on the HMBC here. I think they're a little more convincingly separated than they were in the previous example. So again, just do your best with whatever you've got available to you at this time. So we'll say that B correlates to 5, and then it also correlates to 4. Okay, nothing down at the bottom. If we move on to C, C seems to correlate to 3 and nothing else below it. If we look at D, D also seems to correlate to 3, but if we keep following down, it indeed correlates to 1 as well. And then last but not least, we have E, and E seems to correlate to 2. Okay, like I said, alphabet soup, right? Let's make our lives a little bit easier and clear away some of these marks so that now we can focus more on just what the data is telling us. So we don't need the spots anymore. We just need the kind of coordinate pair, if you will, of number and letter to see, okay, this hydrogen is supposed to be within 3 bonds of this carbon. If it's not, then we know we have a problem. So let's dive in and start analyzing. So start wherever you like. I'm just going to start near the top. Let's look at that A to 6 correlation. I'm going to use a third color to kind of help highlight which bonds we're counting at any given time. And then I'll erase those so it doesn't get too just overwhelmingly messy. But let's get started looking at A to 6, and we'll just do them on both isomers at the same time. And then if it seems like, oh, one might be missing that correlation, we're going to be leaning toward the other isomer. Okay. So starting at hydrogen A and going to carbon 6, if we look on the top isomer, we start here, there's 1 bond, and here's 2 bonds from hydrogen A to carbon 6. Okay, so For the top structure, that checks out. It's a 2-bond correlation. Let's see about the bottom structure. If we find HA and draw down here, we get 2 carbon 2 and then one more across goes to carbon 6. Okay, so same thing here. So that A6 peak checks out for both of our structures. I'm going to remove my annotations and say, yep, A6 works for both of these. That's not really a puzzle piece that's going to tell us anything. Let's move on to B and 5. If we look here on our top structure, coming down from B and then going over to 5, we can see that looks like another 2-bond correlation. And very similarly on the bottom isomer, B2, 5 as well. Very, very similar. It's not telling us any different information. It checks out for both of our isomers. Let's look for B to 4. Starting on our top isomer, if we come from B down to 3, and then we go past this oxygen over to carbon 4, now we see a 3-bond coupling that does check out for our top isomer. Let's see if it's the same for our bottom isomer. So from B, we go down 1, over this way. So that's 3 bonds, 4 bonds. It took us 5 bonds to get from B to 4. So that seems a little bit suspect. I'm going to erase these annotations and then make a note on our bottom structure that the B4 correlation doesn't seem to add up. Let's check out the rest of these to help identify if the top structure is our correct isomer. And we'll leave a little question mark by the B4. Okay, C23. Let's see about that. On our top structure, C coming down, over and over again. C3 checks out for the top one. And then on the bottom one, looks like we might be in trouble again. We go from C to 3. It's taking us, again, 1, 2, 3, 4, 5 bonds to do it. That also seems pretty suspect. So let's add that to the list of factors that don't add up for our bottom molecule. Not looking too good. Let's keep practicing through with the rest of the pieces just so that we can see how they work. Okay, D to 3. If we start on the top isomer from D, we go to carbon 5 and then over to carbon 3. That's a 2-bond coupling, not so bad. And then on our bottom isomer, it's very similar, 3 to 5. That is a 2-bond coupling for both of those. That one checks out. Now let's look for E to 2. On our top isomer, if we take this bond here and then over 1, we get from E to 2, no problem, 2-bond coupling. And it looks like the same will be said for the bottom isomer. We go from E to 2. It only takes 2 bonds to do for either of those, so that one checks out. Okay, only 2 more peaks to go. If we look down here at the bottom for A1, we want to take hydrogen A and see if we can get to carbon 1 within 3. So we go 1, 2 over the oxygen, and 3 to get to carbon 1. Now on the bottom, if we start at A, come down, there's 1, 2, 3, 4, 5. So that's not close enough. It seems that that one won't work out either. Let's erase those annotations and say that the A1 here, also not good. Last but not least, let's check the D to 1 coupling. If we start on the top structure, here's D to 5 and then over to 1. That checks out, no problem. And D to 1 on the bottom looks very similar as well. So that one checks out, but the overwhelming amount of evidence here shows that this isomer is missing those correlations, that B isn't close enough to 4, C isn't close enough to 3, and A isn't close enough to 1. So because of that, I think we can effectively rule out our methyl ester isomer. You can tell how difficult it would have been to decide between these 2 isomers because both of the one-dimensional NMRs are going to look very similar. Even something like your HSQC doesn't really give you the full picture because we could draw both sets of annotations for either isomer and neither of them looked wrong or right. They just seemed to match up pretty well with the data that we were given. So that's why this HMBC technique can be really useful when you know what the pieces are, but you're just not exactly sure how they're connected. So this, again, will not be required for your post-lab assignment, but there are a few practice problems that contain HMBC data that may be helpful for you to practice with. So stay tuned for the next two videos where we work through a full spectral assignment to kind of take the pieces of one-dimensional NMR, COSY, and carbon-hydrogen HSQC analyses, bring them all together, and really dig through the data to give us a full assignment of carbon and hydrogens on molecules that are still relatively small, but more complex than the examples we've looked at so far. These will be great practice for your post-lab, as that's essentially what we're asking you to do for that assignment. Let me know if you have any questions. Stop by office hours or leave a comment. Thanks for watching.